Good day, everybody. I think you were supposed to hear another talk here. I'm in a replacement. And, oh, see, many people coming. Please go on. My name is Luca, and my day-to-day life, I work as an AI engineer. And I suppose, like in the past, well, more than a year now, you might have seen something that looks like this, right? A chat with a model that has some nice snippets into it. When you log into ChatGPT, to Kimi, to Gemini, or Perplexity, even, you might be seeing something more nuanced that you were used to be seeing when you were chatting with models a couple of years ago. You see models that perform searches. You see models that, let's just say, show step by step the reasoning. They show you what is called like an interleaved thinking pattern, whereby you can see what they're going through. And if we go actually a bit more on the like real demo side, you can really see that they models perform steps called tools, show you like an initial plan of what they're trying to do, or even more, they can see like show you all the web pages they search. But I think we went through this already. And then they start seeing or even leaking some kind of these steps. Can you provide the internal reasoning so they can create the title? You see summaries of what the model is going through. All of this is something that has been made possible in giving some recent strides, fairly recent. In the LLM era, this might be prehistoric, I would say, that like came out in a couple of years ago, like summer last year, when somebody, not of the last year, sorry, the previous year again, when we were start talking about the secret sauce, the secret model that OpenAI was working on, which was ChatGPT O, the O series. Anyone heard of them, right? Okay, yeah, see, yes, so many people nodding. So today, and especially in the next 25 minutes, we would like to bring this from like a isolated perspective to something more grounded, like in a more, I would say, even scientific way. We'd like to go through a couple of steps where we were at when OpenAI started thinking of these reasoning models, and basically why we stopped there, and why was this phase was preceded by a sort of a lack of enthusiasm for where AI was going. And then we'll be talking about, let me say, char crimes or the performances of these models as they were first reported when they were launched, and take a bit of a detour to just briefly understand that that part of the research was not like invented in 1 year of OpenAI doing the research, but has like actually a much longer history in the papers. And so finally, we'll try to speculate what at the time was the special architecture of O1 and what we now know, and what kind of possibilities like were made possible, when were made available to the rest of us when DeepSeek released their model. The whole idea of the talk is just to give you a clearer picture of how these models are trained, what's the different sauce that was behind it, and how pivotal, in a way, DeepSeek was, the release of DeepSeek R1 was. Not only in terms of, okay, maybe the Chinese have caught up onto us, but also in terms of, hey, they showed us like a reproducible recipe to achieve what was just touted as a like a grandeur moment that was, of course, like kept private for, in a way, just like the purposes of OpenAI defending their competitive advantage against the others. 22 minutes, let's go. So the goals of this part is to be, as I was saying, be more familiar with some concepts of this called test time or inference time compute, and how this has been achieved in the past, and how this could be implemented in reasoning models. But especially like a hypothesis of how OpenAI or one works, or all the O series models, or even now the ChatGPT 5.3, 5.4, whatever, all the Claude models, etc. And especially dig a bit deeper, looking closely at the R1 paper and the model itself, how it was trained, and how like reinforcement learning came back, and how it's been used and improved to achieve this kind of reasoning capabilities in machine learning models. What was going on back in 2020, and to understand this, that's why we need to jump back, is that at first we were thinking that we needed just to make bigger models so that they could achieve and unlock these wonderful capabilities. This led us to a nice era of incredibly large models that everybody forgot about. What if I told you like Megatron by NVIDIA? Did anybody heard of it? Okay, just one. Yes, that's how popular it was, right? And Fun fact, this is why Nemotron or Nanotron by NVIDIA are called this way. Even though they are like, I don't know, maybe 100 billion parameters, Megatron was like either like 500 billion or even 1 trillion parameters. That by 2020 standard was uh, abnormous, way too much. And this led us to a series of very interesting papers. The first one was published by OpenAI, but then also like the more popular version by Hoffman and others, known as the Chinchilla Scaling Laws paper, that was also featuring the current CEO of Mistral as one of its core contributors. The idea of this paper, and you don't have to go through this, but I think the chart to give you the proper intuition is that you see here that if you take the model, you do not need to scale just the parameter size. You also need to increase the data, the amount of data that you feed it for the model for it to train, for probably to achieve the maximum performance possible. So this is not actually like a law that you need to scale the data, but it's more of a budget constraint thing. Given that you have budget C, so you can only spend this much money on your hardware, so to run your GPUs, how can I mix the amount of parameters and the amount of data? And this has led to an idea that is the concept of scaling laws that's been popularized and been recurring anywhere. If some of you were attending the talk that Gabriele and I gave this morning, we were briefly talking about it in the field of interpretability research in AI. Folks at Anthropic managed to scale these machine learning techniques to their explainability models, apply them to much larger models, and they had like a huge section of their papers when they were talking about how they use the scaling laws to make their figure out how much data they will need to put into to be perfect there and achieve the maximum performance out of their methods. This is basically where this was born for the public in the mainstream media. And the idea is that when you have such budget, you need to spend some money in doing some short kind of experiments with much smaller models, mixing the amount of data and the amount of parameters that you want to combine to find out like this local optimum. And if you do this by varying the amount of parameters as well as the amount of data that you find in a model, you will find these curves that are called isoflops curves. So basically, every point along this line has been trained with the same amount, say, of parameter or data. In this case, like the curve that I'm pointing at has been trained on the same amount of data, but you vary the number of parameters and you achieve the loss that's reported on the left side. But the most important part is it shouldn't be like the curve itself, but basically the shape of all of them. All of those have like a local optimum, and all of them slide in the same manner, as if they were following a curve. And the key intuition that was popularized by this paper is that if you do this kind of ablations, you can find that these curves perfectly align along this line, so you can find the coefficient of this line, and this will extrapolate to much bigger lengths. So maybe if you're working with a 6 billion parameter model, the better amount of data that you might want to be using is a to the power of 21. So that amounts to a huge amount of tokens. I can give you just like a rough idea of this. But what's important is not this one, but is that if you draw a line through here and you prolong and you elongate it, whoopsie, I spoiled it. You can see that maybe if you want to train a much bigger model that has these many parameters, you might want to use this amount of data to optimize how you're spending your money. So this is the gist, right? In 2020, we figured out that to better allocate our expenditure given a fixed budget, we might want to spend and invest more in data and less in the number of parameters, to be more scientific about it. And this unlocked like more efficient model building. And this has led to the achievements that we've been seeing up until, I would say, Llama, but also not only that. And this was revolutionary because we did realize that we needed to be, that data was not an afterthought. The data was to be carefully like balanced and as in part of a mixture of a recipe. That's how to make a large language model. And then Meta came and they found out that even like the chinchilla scaling laws, which was the ones I was talking about later, were good, of course, but were not ideal. And the idea behind it is that basically what they figured out was that first, the data that used to train the model is really like poor quality. So you need to filter it out very carefully. And you need to use synthetic data to enrich the amount of data that the model is trained on, especially in the later phases of the model training, so that you get a model that follows your instruction much better. or that it can find new problems, or that you can take data from, I don't know, a textbook and generate pairs of questions and answers from it, so it can learn the structure, it can learn more concepts that were otherwise would have been just been displayed in just a random pass over an unstructured textbook. But also they found out something that's way more interesting, is that when the scaling laws were designed, or where the paper came out, we were still using those models only as a private, like more in terms of we are still training the models, but we're not using those at scale for like billions of people on your devices. And the key takeaway of what all the studies after that shown was that you need to adjust your scaling laws to the cost of inference, because ideally, yes, maybe the data shows that it's ideal to have a mixture of, I don't know, 100 billion parameters with a trillion tokens of text. But maybe if you want to run that and have a certain like an acceptable latency that you want the user to access to, or you promise users to have to, you need to train a much smaller model on much more data or for much longer, and to find yourself in a suboptimal spot when it comes to how much you spend your money, because you need to make it smaller and make it learn more in a suboptimal way. And this has led to a nicer series of findings, especially from the former Mosaic AI company that was later bought by Databricks, is that actually you can still train the model for far longer. And you see here, this is logarithmic scale. So you can go, maybe you can train like a small model that contains 2 billion parameters or even less. And you can train those with 3-4 times as many tokens, so per parameter, which is just a rough measure to say how much data we go for each parameter in the model, and still see that the performance is decreasing, is like the loss is decreasing, so the model is improving. So the idea is, yes, scaling laws are a matter of compute efficiency, but they're not like the right way to train the model if your goal is inference, serving the models and make it available on your devices. And this basically brought us to the situation where we are now, where we are training models with much more data and making them a bit smaller to run them faster, to run them in a more cheap way, given like the demand is so big. And if you look at, for example, the models that came out from Liquid AI, that's a small company, Maxime Labon is working there, I think he's a quite popular figure, so you might have heard of him. They are models that have like a couple billion parameters at most, but ideally up to like hundreds of millions that are trained on 38,000 billions token of text. This amount, like they blow these new numbers in the dust. So why do we do it? The question is, do we have that much data? Yes, of course, we know we do it. Data has never been a problem. We were worrying whether we would like finish the data to train the models on. We do have that amount of data because we can use models to enrich it, to rephrase it, even when the model itself is being trained. But we are hitting diminishing returns, because if you look at the curves, they're going slower. The loss is decreasing slower and slower. So what's the payout for that? And this is why we were a bit skeptical back in 2024 about where this model release after model release was bringing us, until ChatGPT 01 preview came out. And this was built on a really stunning conclusion, actually not conclusion, but realization, is that the cost of inference has been dropping like for orders of magnitude. So maybe, what if we take the same intuition that the people from OpenAI had, actually from Meta had, to train a smaller model to run with on more tokens, because this makes the model cheaper to run, because the hardware is cheaper. What if we find a way to make the model generate more text before it just spits out an answer? We can train a smaller model that is more clever, that generates more text, that is capable of reasoning or just structuring a process before spitting out the final answer. So we can invest a bit less or spend a bit less in terms of modeling, and maybe spend more when we actually run the model. And this is basically the whole premise behind OpenAI 01. That when it came out, it did it with an obscure manner, like in the most obscure manner possible. And what they're doing here is to say, hey, we don't give you the scale, we don't give you how much this costs you, but if you go from one step and you generate 10 times as many tokens, with this new kind of model, you get the performance going from, I don't know, 25% up to 80%. Which was bonkers, because in a way, we found out the ways that the models, and you can see way better here, ChatGPT models like ChatGPT 3.5 and ChatGPT 4 that were there on this different benchmark weren't even included in this chart, because back in the days they were like well below 5%. And this benchmark, which is, just to put you like briefly, is a technical benchmark that contains the, like eye level, PhD level kind of questions that weren't released publicly, only just a subset of those because they want to preserve the benchmark from contamination. We went in basically 3 months from '01 to '03 to go from 7% of accuracy to 88%, just because the model could reason. So spit out more tokens, think about the process that it was going to do, maybe call some tools into it, and finally give the answer. And this has skyrocketed the performances of these models by several order of magnitudes, saturating the benchmark. Unbelievable, but also very expensive if you think about it, because here to get 88% performance, you're going very well in the $1,000, maybe $3,000 regime to just to get an answer to a question that maybe the average STEM grad that can be paid like $10 an hour could just give out for and perfectly. So this is always, of course, I think a matter of trade-offs. But to be able to go from here to here just by like doing 10 times as many, spending 10 times as much, well, that's a remarkable achievement. So how was this done? This is something that wasn't like new. This is something that we've been trying to experiment with even ourselves well before ChatGPT came out. Remember, this paper is from 2021. ChatGPT came out in 2023 or maybe 2022, whatever. But it predates ChatGPT, right? And just the way of saying, hey, think step by step before giving an answer. Basically, what these papers show us is that we can take this reasoning approach, this think before answering, and make it structured and make it bake into the training procedure. And so I digress and just go really briefly over this one. What we can do is that, for example, we can train a model that generates n answers, and then we use an algorithm or just another model that ranks the best answer that it gets, and then we pick that one. This is a kind of a way to use your inference budget more so that you can just use the model once, have it generate multiple answers, and then have another model that picks the best one. You're not doing this during training yet. Or you can make this search a bit more refined and have the model output steps, and then have another verifier. This is what is called this external model or algorithm that verifies that gives a score to your reasoning, and have it like verified individual steps and just prune the needless branches and go on. Alternatively, you can do something a bit more sophisticated, which is to boom, 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 boom. There we go. Okay, let me just skip this through. Okay, you can do something different and have maybe the model, rather than have it generate during the training, immediately the answer, have it generate a turn one response and then feed this back with the prompt inside the model, and have it maybe even also like a feedback or an output or like the output of a tool call, and feed it back before it generates yet another response. And so instead of just having the model be trained to spit out text, or instead of doing what I was showing you before, to have the model generate multiple answers and then have another model pick the best one, maybe what you can do is train a model that thinks, that outputs intermediate steps, that is trained to output these steps of the reasoning before finding the final answer. And I think that this kind of feels familiar to most of you in a way, because this is what we're seeing with ChatGPT when we use it. And OpenAI was always obscure about this, and we found out so many conflicting evidence, tweets, blog posts about, oh, they must be using parallel sampling. Oh, they must have trained the model to think. And this was a lot of stuff. And even like Claude 3.7 had this kind of reasoning thing for a while before they released their official model. And even the OpenAI documentation included this when they were explaining how reasoning works. That is basically the same thing I will show you in the other slide. So everybody was like, oh, this must be it, right? And so we were still thinking about what was going on, how they do it, etc., until DeepSeek came out and gave us like a proper answer to this. What is DeepSeek? There's it's a Chinese lab. Mistral folks like mind control me there. And they published banger after banger in 2024 about small models, very strong ones, until like in January 2025, they came out with this R1 paper. NVIDIA stock fell, and we were like, "Oh, what is this?" And basically, what they did is that they showed us how to properly train our reinforcement learning model, and basically the recipe that they've shown has been replicated to every basically other open source reasoning model, and we are pretty confident that what they showed is what basically the biggest AI labs are doing. So what do they do? Well, they introduce a new step in the training procedure of a reinforcement of a big large language model, which is using reinforcement learning, but a flavor of reinforcement learning that's called reinforcement learning with verifiable rewards. And this means the first part that I was showing you, like grading the answers, like the intermediate steps, and perhaps just read the final step one, and then update the weights. So train the model not only of like if they guess the word, but if the outcome of what they do is correct. We are shifting the training of the model from just learning how to predict the next word to make it like gauge the quality of their output. This could be code, and this is fairly easy to implement because you can just, if you output code, you can just use a linter to verify the code is correct. You can run the code to see if it works. You can have the test pass and see, okay, this code covers all the edge cases. So you can bake all of this into your reward function, into the training procedure of the model, and have it be like the model learn this. Not only, oh yes, it has learned that after def I need to put a parenthesis. This is way more sophisticated. And then basically, when you do this, you need to start with some label data and use, but actually, this is a bit more of a sophisticated recipe, but you need to get these examples that the model learns from. Because in the end, you need, of course, you need to train the models to to be able to generate this kind of reasoning traces. But the first step to get a model like ChatGPT 01 or ChatGPT 5.4 or whatever it is to get a small sample of these generic traces that the models needs to learn from. And then what they do is basically take the base model, which could be like a DeepSeek base or could be like any, let's just say, vanilla ChatGPT model. You perform a certain tuning step that's called supervised fine tuning that's just designed for the model to learn to be an assistant, to answer and reply in the shape of, I ask a question, oh yes, of course, I can answer, I can be a provider. Where they can learn, you're absolutely right, and then provide to spit you some nonsense. And after you do this, then you can train it with reinforcement learning with verifiable rewards. So you can ask them like mathematical questions, coding questions, or maybe even essay writing capabilities, and have the model that now has learned to follow instructions and answer that format to get feedback from the data and from all the verifiers that we built. When we do this, we go on yet again with some more supervised fine tuning. And finally, we do another combination of reinforcement learning, the first one with reinforcement learning with verifiable rewards, yet again, and then with the RL from human feedback, HF, which is the one that we do when we want the model to align to the preferences of those people who are training it to become more welcoming, to avoid to be more nice, to avoid giving you immediately an answer to make some, I don't know, chemical drugs in your home. This is where the phase where people train the models to avoid answering to certain domains. So just as a recap, basically what DeepSeek had was a very good base model. Imagine just a vanilla llama or a vanilla ChatGPT, whatever. And then they performed all these steps whereby they had some generation, like they generated somehow some reasoning traces. Some speculated that they took generated data from OpenAI, but we can never verify this. And then we performed like the average supervised fine-tuning rest steps, like the first one and the second block. They were really common in every Llama 2, Llama 3 recipe, but they added this, they sprinkled some reinforcement learning on top through verifiable rewards. So through basically question and answer pairs where the score of the answer was not based on how well you like printed the right words, but based on different criteria that are based on correctness of the code, whether the code is correct, whether the code can run, whether the mathematical result is correct itself, and all this kind, or even just other LLMs gauging the quality of the output in terms of like text. And finally did this twice, basically, before reinforcement learning. And this is how they got DeepSeek R1. Where does this leave us? Well, basically what has been going on in the past year or so is that we scaled reinforcement learning more and more. And now that we have strong base models, this is incredible because we can see how much stuff we can use them for. The Kimi website I was showing you before has been basically, I asked them to prepare a presentation with slides, which was unheard of. I mean, of course, we were thinking about it, but like 1 year and a half ago, it wasn't possible, right? And ideally, oh my God, I thought I had some more charts. Oh, that's very sad. But the point is that we are now seeing people using much more this reinforcement learning and pushing it to generate new data. Not more than new data, but new capabilities, and extend it to different domains, and doing more and more and more yet again reinforcement learning, whereby it's taking up so many more steps in the training pipeline. Whereas we are training these models on much more of these problems rather than text generation, or like rather than generating new text or the correct text, we generate text and evaluate based on these new scores. And this is becoming like the predominant part of how we train the models. Like we spend much more computing this kind of problem solving setting, and this is how we teach the model to reason. And this brings us back to the original point, which was this is making us the model not rather learn the concepts, not rather than being an encyclopedia or building like the knowledge of what is going on, but it's learning how to use the tool that we make it available to it. And this means that we are learning models a bit less to be like a memory bank or a dictionary, but more like, I wouldn't say not dumb, because they're not dumb. They know less facts, but they know how to use tools more. This means in terms that we have longer generation, they generate more text, but this is all like learning how to generate the intermediate steps to achieve and get the information that you need to train, like to achieve your conclusion result. And this basically was all of it in a nutshell. Might be a lot, but if you have any feedback, I would like for you to share it with me. Thank you very much. Vabbè, dai.